Here's what nobody tells you about teenage STEM education. The colorful kits, marketed as advanced learning, are mostly expensive toys wearing lab coats. Real engineering skill building looks completely different, less like edutainment, more like actual apprenticeship. I'm Chloe Miller, and I've spent years evaluating what actually prepares teenagers for technical careers versus what just looks impressive on a shelf.
You're listening to the STEM Lab podcast. Quick transparency note before we go any further. Everything you're hearing, the research, the analysis, the script, that's all human verified and written by real authors. The voice delivering it, though, that's AI generated, just so you know exactly what you're getting. If you've been listening for a while, thank you. Seriously, knowing people keep coming back makes this whole thing worthwhile. And if you're new here, welcome. Glad you found us. We drop new episodes every Monday, Wednesday, and Friday, covering what actually works in STEM education for teenagers, not just what marketing departments want you to buy. Let's get right into it. If your teenager can design parametric CAD models, write Python scripts that control hardware, or collect calibrated environmental data, they're not playing with STEM, they're building a technical resume. That's the standard we should be aiming for, measurable competencies that translate directly into industry tools, competitive portfolios, and the kind of hands-on fluency colleges and employers recognize instantly. So what exactly counts as meaningful STEM work for teenagers? We're talking about structured, project-based learning experiences that develop actual technical competencies in science, technology, engineering, and mathematics. Unlike elementary kits focused on exploration and wonder, teenage STEM work emphasizes industry-standard tools, reproducible methodology, and transferable skills. These activities bridge the gap between guided tutorials and independent problem solving. Your teenager isn't just following instructions, they're debugging code, iterating designs based on test data, making engineering trade-offs with real constraints like budget, material properties, power consumption, and time. Picture this: programming a microcontroller to log temperature data every 5 minutes and graph trends in Python, not clicking through a colorful app that congratulates you for coding. The defining characteristic here is real-world applicability. Activities should mirror workflows that professionals actually use: version control for code, parametric modeling in CAD software, sensor calibration protocols, proper design documentation. When your daughter writes Arduino C++ to control a servo motor, she's using the same IDE and syntax an embedded systems engineer uses every day. When your son models a mechanical linkage in Fusion 360, he's working in a platform industrial designers rely on daily. Progressive STEM activities also demand accumulating complexity. Early projects establish foundational skills, blinking an LED, printing a calibration cube. Middle projects integrate multiple systems, maybe a sensor-triggered alarm with data logging. Advanced projects require original problem solving, designing a custom circuit board, optimizing wind turbine blade geometry through iterative testing. Now, let's talk about how effective STEM activities actually work. They follow a 4-phase cycle: specification, implementation, validation, and iteration. This isn't busy work, it's the engineering design process compressed into accessible projects. Every meaningful project starts with a clear objective and constraints during the specification phase. Build a robot is way too vague. Program a line-following robot that navigates a track in under 30 seconds using infrared sensors and PID control gives your teenager concrete success criteria. You'll notice real STEM activities include measurable outcomes, data accuracy thresholds, structural load requirements, code execution speed, energy efficiency targets. For coding projects, specification means understanding inputs, outputs, and edge cases before writing a single line of code. If your teenager's building a weather station, the spec might be: collect temperature, humidity, and barometric pressure every 10 minutes, store data locally on an SD card, transmit hourly averages via Wi-Fi to a cloud dashboard, run continuously on solar power with battery backup. Each requirement forces technical decisions downstream: sensor selection, power budget calculation, data format design. During implementation, platform choice matters intensely. Arduino-based projects teach C++ fundamentals and bare metal hardware control. You're directly manipulating registers, managing memory, thinking in microseconds. Raspberry Pi projects introduce Linux environments, GPIO libraries, and higher-level languages like Python, which opens doors to data science, machine learning, and web integration. For robotics, platforms like Vex V5 or Lego Spike Prime offer block-based or text-based programming with industry-relevant sensors and actuators. Here's what really matters. Does the kit require proprietary software that locks you into a walled garden, or does it work with open-source tools? The Arduino Mega 2560, check the show notes for a link to the current price, runs on Arduino IDE, which works on Windows, Mac, or Linux, works offline, and stays free forever. It integrates with Platform I/O for professional-grade development. That's a platform investment. Closed ecosystems with subscription-based cloud IDEs teach kids to depend on someone else's server staying online. For 3D printing projects, your teenager learns slicing, converting models to G-code, support structure strategy, material selection, PLA for prototypes, PETG for mechanical parts, TPU for flexible components. They learn print parameter tuning. The Creality Ender 3 V3 SE, again, current price in the show notes, teaches these skills on a machine architecture that's ubiquitous in makerspaces and small manufacturing. You're not just making trinkets, you're mastering a fabrication process engineers use every single day. The validation phase separates STEM theater from STEM work. Does the robot follow the line? Does the wind turbine generate the predicted voltage at a given RPM? Is the temperature sensor reading within plus or minus half a degree Celsius of a calibrated reference thermometer? Your teenager learns to collect data systematically, identify failure modes, distinguish between code bugs, hardware faults, and design flaws. This phase also teaches documentation discipline, keeping a lab notebook with time-stamped observations, annotated code commits, photo documentation of iterative builds. That's how professional engineers work. It's also how science fair judges, scholarship reviewers, and college admissions officers distinguish serious STEM students from hobbyists.
Real engineering is revision, and that's what the iteration phase is all about. The first design always has problems. The motor stalls under load, the sensor drifts after an hour, the 3D printed bracket flexes too much. Iteration teaches your teenager to analyze failure, hypothesize solutions, implement changes, and retest. This loop, fail, diagnose, fix, validate, builds the resilience and systematic thinking that separates someone who likes science from someone who can actually engineer solutions. Advanced projects add optimization challenges. Can you reduce power consumption by 30%? Can you halve the code's memory footprint? Can you redesign the structure to use less material while maintaining strength? These constraints force creative problem solving and deepen technical understanding far beyond tutorial following. Here's why all this matters. Teenage STEM activities are career capital, not metaphorically, literally. A 16-year-old who can demonstrate a GitHub portfolio of Python projects, a portfolio of parametric CAD designs, or documented science fair research has already separated themselves from 95% of college applicants. When your teenager masters Arduino, they're learning the Atmel AVR microcontroller architecture that powers millions of embedded systems. When they write Python data analysis scripts, they're using the same language that dominates machine learning, bioinformatics, finance, and climate modeling. When they model in Fusion 360, they're building skills that transfer directly to SolidWorks, Rhino, and other professional CAD platforms. These aren't educational approximations, they're the actual tools. I've watched this play out in my own work. The solar charge controller I built at 17 used the same Arduino-based MPPT algorithms I later adapted for a community microgrid project. The skills compounded because the foundation was real. Colleges and scholarship committees see thousands of applications listing STEM club and robotics team participation. What stands out is specificity, designed and programmed an autonomous greenhouse monitoring system using ESP32 microcontrollers, DHT22 sensors, and Python data visualization, reduced water waste by 40% in school garden. That sentence demonstrates systems thinking, interdisciplinary integration, and measurable impact. It's not resume padding, it's proof. And looking ahead, the next decade demands engineers, scientists, and technologists who can build sustainable systems at scale. Teenage STEM activities focused on renewable energy, environmental monitoring, and resource efficiency aren't just feel-good projects, they're on-ramps to the fastest-growing sectors in engineering. Learning to measure solar panel efficiency, calibrate air quality sensors, or optimize wind turbine designs teaches both technical skills and systems-level thinking about energy, ecology, and resilience. That combination will define the most impactful careers of the 2030s. Let's break down 6 core categories of teenage STEM activities worth investing in. First, microcontroller programming and electronics. Arduino, Raspberry Pi, ESP32, and microbit platforms teach circuit design, sensor integration, and embedded programming. Projects range from simple LED control to complex IoT systems with cloud connectivity. Key milestones include reading datasheets, writing interrupt-driven code, debugging with serial monitors, and designing printed circuit boards. You'll need a 5-volt power supply, USB or wall adapter works fine, breadboards, jumper wires, and a multimeter for troubleshooting. Expandability is key here. Look for platforms with large component ecosystems and active community support. Arduino and Raspberry Pi both excel in this area, while proprietary platforms often don't. This work connects directly to careers in embedded systems engineering, IoT development, hardware prototyping, and robotics programming. Second category, 3D design and additive manufacturing. CAD modeling and Tinkercad for beginners, Fusion 360 for intermediate to advanced work, or FreeCAD if you want open source options, all combined with FDM 3D printing. Projects evolve from downloaded models to designing functional mechanical parts with precise tolerances and engineering fits. Skill milestones include parametric modeling, designs that adapt when you change dimensions, assembly constraints, stress simulation, slicing parameter optimization, support structure strategy, and post-processing techniques. You'll need dedicated space with ventilation because even ultrafine PLA filament emits ultrafine particles. Plan for stable power and dry filament storage. Budget $300 to $500 for entry-level machines. Enclosed printers add safety for ABS and PETG printing. Consumables are ongoing, figure $20 to $30 per kilogram of filament. This prepares teenagers for careers in mechanical engineering, industrial design, product development, aerospace, and biomedical device design. Third, robotics and autonomous systems. Platforms like Vex, First Robotics, Lego Spike Prime, or custom Arduino-based builds integrate mechanical design, sensor fusion, motor control, and autonomous navigation algorithms. Competitive robotics adds time pressure and strategic thinking. Important milestones include PID control loops, odometry and localization, path planning algorithms, real-time decision logic, and team collaboration with documentation. You'll need ample floor space for testing, charging stations for lithium polymer batteries, basic tools like screwdrivers and wire strippers, and software that works on Windows or Mac for most platforms. This connects to careers in robotics engineering, autonomous vehicle development, industrial automation, and AI/machine learning engineering. Fourth category, data science and machine learning. Python-based projects using libraries like NumPy, Pandas, Matplotlib, scikit-learn, and TensorFlow. Activities include data cleaning, statistical analysis, visualization, and training simple machine learning models. Real datasets, climate data, environmental sensors, public APIs make this tangible instead of abstract. Skill milestones include writing Jupyter notebooks, data wrangling and cleaning, exploratory data analysis, training supervised learning models, evaluating model performance, and understanding bias and overfitting. You need a computer capable of running Python 3.10 or newer with virtual environments and Jupyter Lab. RAM matters here, 8 gigabytes minimum, 16 preferred for larger datasets. All the software is free and open source. This prepares for careers in data science, AI and machine learning engineering, bioinformatics, climate modeling, and quantitative research. Fifth, environmental science and citizen research. Citizen science projects use sensor kits to collect water quality, air quality, soil chemistry, or weather data. Activities emphasize calibration protocols, data validation, statistical analysis, and contributing to real research databases like iNaturalist, SciStarter, or Glub Observer. Key milestones include sensor calibration, quality assurance and quality control protocols, geospatial data collection, longitudinal data analysis, and scientific writing and presentation. Environmental kits require outdoor deployment planning, weatherproofing, power supply with solar and battery backup being common, data logging via SD cards or wireless transmission, and periodic maintenance. Sensors need calibration against known standards, or you end up with junk data. This connects to careers in environmental engineering, climate science, ecology, public health, and geospatial analysis. Sixth category, renewable energy engineering. Hands-on projects with solar panels, wind turbines, and energy storage systems. Activities include efficiency testing, power electronics like charge controllers and inverters, system design with load matching, and optimization experiments. Skill milestones include measuring voltage, current, and power under varying conditions, understanding maximum power point tracking, designing hybrid systems, and calculating levelized cost of energy. You'll need a multimeter, variable resistor loads, a lux meter for solar work, an anemometer for wind projects, and an oscilloscope for advanced work. Outdoor testing space is essential. Consumables are minimal beyond replacement parts for iterative turbine blade designs. This prepares teenagers for careers in renewable energy engineering, grid systems design, sustainability consulting, and power systems optimization. Now, throwing your teenager into an advanced robotics platform without foundational skills wastes money and kills motivation. Effective STEM progression builds capability milestones systematically, with each project reinforcing prior skills while introducing new complexity. For electronics and programming, start with Arduino starter kit projects during months 1 through 3, blinking LEDs, reading buttons, analog sensors, serial communication. The goal is understanding circuit basics, writing simple code, and debugging using the serial monitor. Months 4 through 6 bring intermediate work, multi-sensor integration, motor control, interrupt-driven programming, basic state machines. A good project example would be a temperature-controlled fan that logs data to an SD card. The goals are managing multiple inputs and outputs, writing modular code, and using libraries effectively. Months 7 through 12 tackle advanced topics, custom circuit board design using EasyEDA or KiCad, wireless communication via Wi-Fi or Bluetooth, integration with cloud platforms, real-time operating system concepts. Project example, an IoT environmental station with a web dashboard. The goal shifts to designing complete systems, not just prototyping breadboard circuits. For CAD and manufacturing, months 1 and 2 cover Tinkercad basics, extrusions, holes, grouping, alignment. Print downloaded models to learn slicing and print settings. The goal is spatial reasoning, basic 3D manipulation, and understanding how print orientation affects results. Months 3 through 6 introduce Fusion 360 parametric modeling, sketches, constraints, dimensions, extrusions, revolves, assemblies with joints. Design functional parts like replacement brackets, custom enclosures, mechanical linkages. Goals include engineering fits with proper clearances and tolerances, plus design for manufacturing principles.
Month 7 and beyond brings stress simulation, topology optimization, multi-body assemblies with motion studies, and surfacing for organic shapes. A good advanced project? Design and test a gear reduction system or articulated mechanism. The goal is professional CAD fluency and an iterative design test revise workflow.
For data science, months 1 and 2 establish Python basics, variables, loops, functions, lists, dictionaries. Work through Codecademy or Free Code Camp. Goal: read and write simple scripts without needing tutorials. Months 3 through 6 introduce NumPy arrays, Pandas data frames, and Matplotlib plotting. Use real datasets like weather data or sports statistics to practice. Project example: analyze 5 years of local temperature data, identify trends, create visualizations. Goals include cleaning messy data, computing statistics, and creating publication quality graphs. Month 7 onward covers scikit-learn for machine learning, Jupyter Notebooks for reproducible research, and version control with Git and GitHub. Project example: train a model to predict energy consumption based on weather data. Goals include understanding the machine learning workflow, evaluating models critically, and documenting code professionally. Setting up effective workspace makes the difference between consistent skill building and sporadic frustration. Teenage STEM activities demand more than a kitchen table. You need dedicated space, reliable power, proper tools, and organizational systems. At minimum, you need a 4 by 6 foot desk area with task lighting, a power strip with surge protection, and storage for components and tools. Preferred setup: dedicated 8 by 10 foot space with a workbench, overhead lighting, pegboard tool organization, shelving for projects in progress, and a fire extinguisher rated for electrical fires. For 3D printing, add a 2 by 2 foot footprint for the printer itself, ventilation like a window fan at minimum, with HEPA filtration preferred, and a fire-resistant surface. For robotics, include 6 by 6 feet of floor space for testing. Power and connectivity essentials include a 15-amp dedicated circuit with at least 6 outlets, stable Wi-Fi for downloading libraries and documentation, but with offline capability for core tools, Arduino IDE, Fusion 360 offline mode, Python with local environments. Here's a cloud-dependent pitfall to avoid. Platforms that require constant internet for basic functionality, cloud IDEs that won't compile code offline, subscription-based services that lock projects behind paywalls, proprietary ecosystems that disappear when companies pivot. Choose tools with local-first design. For electronics work, you need a digital multimeter, soldering iron with adjustable temperature, 60 watts minimum, helping hands, wire strippers, flush cutters, breadboards, assorted jumper wires, and resistor and capacitor kits. Budget $80 to $120 for quality basics. For 3D design and printing, an FDM printer running $300 to $500. Digital calipers accurate to plus or minus 0.01 millimeters. Scraper set, needle nose pliers, hobby knife, sandpaper assortment, and filament storage using dry boxes or vacuum bags with desiccant. Budget $400 to $600 startup, $30 to $50 monthly for consumables. Data science needs a computer with 16 gigabytes of RAM, dual monitors, that's a productivity multiplier, a mechanical keyboard for ergonomics during long coding sessions, and a backup drive. All software is free and open source, so budget zero beyond hardware. For ongoing consumables in electronics, components wear out, LEDs burn out, sensors fail, wires break. Budget $20 to $40 monthly for replacement parts and expansion components. For 3D printing, expect filament at $20 to $30 per kilogram, nozzle replacements at $5 to $15, build surface refreshes at $10 to $20, and occasional extruder parts. Figure $40 to $60 monthly for active projects. Good news: quality STEM platforms like Arduino, Fusion 360 for students, Python, and KiCad are free or one-time purchases. Avoid kits that lock you into monthly fees for basic functionality. Isolated projects teach isolated skills.
Integrated curricula build systems thinking, the ability to see how mechanical, electrical, software, and data components interact. Consider a solar-powered weather station as a cross-domain project example. This single project integrates multiple STEM domains. The energy system component involves solar panel selection, charge controller design, battery capacity calculation, and power budget optimization. It teaches renewable energy principles and electrical engineering. Electronics integration includes microcontroller programming on Arduino or ESP32, sensor integration with DHT22 for temperature and humidity, BMP280 for barometric pressure, plus a rain gauge. You're learning I2C communication protocols and power management like sleep modes to extend battery life. The data science component covers logging time-stamped data to SD card or cloud database, Python scripts for data cleaning and visualization, statistical analysis of weather patterns, and correlation studies examining relationships like temperature versus humidity or barometric pressure versus weather changes. Mechanical design involves custom enclosure design in CAD, 3D printing weather-resistant housing, sensor mounting considerations like radiation shields for temperature accuracy, and rain gauge funnel design, plus weatherproofing cable entry points. Project management skills develop through breaking complex systems into milestones, documenting design decisions, troubleshooting when subsystems interact unexpectedly, and presenting results clearly. This isn't a weekend project, it's a semester-long investigation that produces genuine technical capability and tangible portfolio material. For curriculum design, spiral progression, revisit core concepts with increasing complexity. First Arduino project, blink and LED. Fifth project, PWM motor speed control. 10th project, PID-controlled temperature system with web interface. The concept evolves from digital output to analog output to closed-loop control, building systematically. Emphasize project portfolios over tests. Assessment should be show me what you built and explain how it works, not multiple choice questions about theory. Documentation, code quality, problem-solving approach, and working demonstrations are the real evaluation criteria. Build failure normalization into curriculum expectations. The first circuit board layout always has mistakes. The first 3D print always needs parameter tuning. Teaching kids that iteration is the process, not a sign of failure, builds engineering resilience. The most valuable outcome of teenage STEM activities isn't the skills themselves, it's the documented portfolio that proves those skills to outside evaluators. For code, every Python script, Arduino program, or data analysis notebook should live in version-controlled repositories with clear README files explaining the project, dependencies, and usage. Employers and admissions committees actually look at GitHub profiles. It's not hypothetical. A teenager with 20 well-documented repositories showing progression from Hello World to complex projects has demonstrated more technical capability than any transcript can capture. Make it actionable practice. Commit early and often. Write meaningful commit messages like fixed temperature sensor calibration offset, not just stuff. Include photos or videos in README files and add open-source licenses to encourage collaboration. For CAD work, platforms like GrabCAD, Thingiverse, or Printables let your teenagers showcase 3D models with renders, print photos, and design rationales. A portfolio with 15 original functional designs, not downloaded toys, demonstrates spatial reasoning, engineering judgment, and iterative improvement. Portfolio strength indicators include showing failed early versions alongside refined final designs to demonstrate the learning process. Document design constraints and how you met them. Redesigned bracket to fit 8mm bolt instead of 10mm, reduced material by 30%. Photograph printed parts in actual use. Science fair projects done rigorously become genuine research experience. Document methodology, raw data, statistical analysis, and visual presentation. Convert your display board into a PDF technical report. If the work is strong enough, submit to student research journals or present at regional STEM symposiums. Here's Scholarship Gold, a first-place regional science fair project with documented methodology, reproducible results, and clear real-world application is worth more on college applications than a 4.0 GPA in prerequisite courses. It shows initiative, depth, and scientific maturity. Robotics competitions like FIRST or VEX, hackathons, and coding challenges provide third-party validation of skills. Awards don't just pad resumes, they're concrete evidence of performance under constraints like time pressure, rule compliance, and teamwork. Let's talk about what doesn't work, starting with tutorial dependency. If your teenager can't start a project without watching a YouTube tutorial, they're not building independent problem-solving skills, they're following recipes. Real engineering means reading documentation, searching forums, adapting existing solutions to new contexts. The solution? After foundational tutorials, assign open-ended projects with only specification, no step-by-step guide. Build a device that alerts you when your plant needs watering, has dozens of valid solutions. Struggling through design decisions builds capability. Another pitfall? Collecting kits without completing projects. STEM kit hoarding is real. Parents buy Arduino starter kit, Raspberry Pi kit, robotics platform, 3D printer, renewable energy kit, and teenagers dabble without mastering any single platform. Solution? Choose one primary platform per domain, one microcontroller ecosystem, one CAD program, one programming language, and drive deep before adding breadth. Mastery of Arduino beats superficial familiarity with Arduino plus Pi plus microbit plus proprietary robotics brain. Ignoring documentation and version control is another trap. Teenagers who don't document work lose 90% of its value. That amazing sensor project from 6 months ago, if the code has no comments and the wiring wasn't photographed, it's archaeologically difficult to recreate or explain. Make documentation a deliverable requirement. Code comments, wiring diagrams. Fritzing is great for this. Design decision logs, test data tables. Treat every project like someone else will need to understand and replicate it, because scholarships and job interviews demand exactly that. Watch out for greenwashing sustainability claims too. Many eco-friendly STEM kits are theater, single-use projects with unrecyclable components, solar panels too small to power anything real, or biodegradable materials that require industrial composting, which means landfill in practice. Evaluate sustainability claims critically. Real Green STEM focuses on reusable platforms, repairable designs, open-source hardware which extends product life through community support, and projects that actually measure environmental impact with calibrated instruments. Teenage STEM activities should build skills employers and graduate programs actively seek. Here's what matters. High-value industry standard tools include Arduino IDE, Python, Fusion 360 and SolidWorks, Git and GitHub, MATLAB or Octave, Linux command line, CAD/CAM workflows, and oscilloscope fluency. Low-value tools include proprietary block-based languages that don't transfer, closed ecosystem platforms, and drag-and-drop no-code tools that hide actual logic. The difference? Arduino C++ translates directly to professional embedded systems work. Proprietary robot-specific block coding doesn't transfer anywhere. Choose platforms that teach general principles, not brand-specific interfaces. Employers care less about what you built than how you approached problems when it didn't work. GitHub commit history showing debugging progression, documented design iterations with rationale, or science fair journals with failed experiments included all demonstrate engineering mindset. The most interesting careers happen at intersections: biomedical engineering, climate data science,
renewable energy systems, environmental robotics. Teenagers who can demonstrate projects integrating mechanical plus electrical plus software plus data have distinctive competitive advantage. Example: designing an automated hydroponic system requires mechanical structure via CAD and 3D printing, electronics with sensors and pump control and microcontroller programming, data science for growth rate analysis and nutrient optimization, and systems thinking about water and power budgets and failure mode analysis. That's engineering resume gold. Technical skills mean nothing if you can't explain them. STEM activities should include presentation components, explaining code to non-programmers, presenting science fair research to judges, documenting projects in clear technical writing, creating demo videos. This is where science fairs, maker fairs, and teen tech talks build crucial soft skills. Moving to some common questions people have about this topic. What are the best STEM activities for teenagers who've never done technical projects before? Start with Arduino-based electronics projects using a comprehensive starter kit. They provide structured learning with immediate visual feedback. LEDs light up, motors spin, while teaching foundational programming and circuit concepts. Look for kits with offline-capable software, since Arduino IDE works without internet, detailed tutorials for the first 5 projects, and expandability with standard components. After mastering basic sensor input and motor output, transition to integration projects like a temperature-controlled fan or automated plant watering system. Pair electronics work with beginner CAD using Tinkercad, which is completely free, browser-based with a gentle learning curve. You can progress to functional part design within 6 to 8 weeks. The key is choosing platforms with massive community support. Arduino and Tinkercad have millions of tutorials, forum posts, and example projects, so teenagers never get stuck without resources. How much should you budget for meaningful teenage STEM activities that build real skills? Plan for $800 to $1,200 for comprehensive first-year setup across multiple domains. $200 to $300 for a quality Arduino starter kit with breadboards, sensors, motors, and components. $300 to $500 for an entry-level 3D printer like Creality Ender Series or Prusa Mini. $100 to $150 for essential tools, multimeter, soldering station, calipers, hand tools. $200 to $300 for computer upgrades if needed, with 16 gigabytes RAM minimum for CAD and data science work. Ongoing consumables run $50 to $100 monthly: 3D printer filament, replacement electronic components, project-specific materials. Most core software is free: Arduino IDE, Python, Fusion 360 with free educational license, KiCad, so avoid platforms requiring subscriptions. This investment spreads across multiple years and dozens of projects, making per project cost under $50 after startup, which is dramatically better value than one-time project kits that teach isolated skills and then gather dust. Can teenagers really learn professional-level engineering skills at home, or do they need formal classes? Teenagers absolutely can reach professional competency through self-directed home learning. I taught myself to code and design solar systems entirely outside formal education, and the engineers I collaborate with today come from wildly diverse learning backgrounds. The critical factors are access to industry-standard tools like Arduino IDE, Python, and professional CAD software, project-based learning with clear capability milestones instead of passive video watching, and systematic documentation that forces articulation of problem-solving approaches. Formal classes provide structure and deadlines, but often use educational-grade tools that don't transfer to industry. Home labs using actual Arduino, Raspberry Pi, and Fusion 360 teach the exact platforms working engineers use daily. The portfolio and demonstrated capability matter infinitely more than the setting where learning happened. A GitHub repository with 30 documented projects proves more than any transcript. That said, hybrid approaches work well. Use progressive learning path frameworks to structure homework, supplement with online communities like Arduino forums or Reddit's Arduino and 3D printing communities, and pursue external validation through science fairs and competitions. How do you know if a STEM kit or platform will actually prepare your teenager for college STEM programs or careers? Evaluate platforms using 3 criteria: tool transferability, expandability, and professional adoption. Tool transferability means the software, programming languages, and workflows directly match industry standards. Arduino C++ is used in embedded systems engineering. Python dominates data science and machine learning. Fusion 360 transitions seamlessly to SolidWorks. If a platform uses proprietary block coding that doesn't convert to text-based languages or closed ecosystems with subscription-dependent cloud tools, it's teaching platform-specific skills, not transferable competencies. Expandability means your teenager can add sensors, integrate with other systems, and scale projects in complexity. Arduino and Raspberry Pi excel here with thousands of compatible components and libraries. Closed educational robots with fixed sensor sets hit capability ceilings quickly. Professional adoption means the platform appears in actual job postings and research papers. Search Arduino Embedded Systems Engineer or Python Data Scientist, and you'll find thousands of positions. Search proprietary educational platform names, and you'll find elementary school teacher job postings. What's the difference between STEM activities for teenagers versus activities for younger children? Teenage STEM activities emphasize industry-standard tools, open-ended problem-solving, and measurable technical outcomes rather than guided exploration and play-based learning, while elementary STEM focuses on wonder, engagement, and foundational concepts through structured kits with clear instructions. Teenage work demands debugging code without step-by-step tutorials, iterating designs based on test data, and making engineering trade-offs with real constraints. The progression looks like this. Elementary students use visual block coding in fixed environments, like Scratch or Lego WeDo. Middle schoolers transition to block-to-text bridges, like Lego Spike Prime with Python option, or Blockly with JavaScript visibility. Teenagers write production code in text-based IDEs with version control and documentation discipline. Similarly, younger children assemble pre-designed mechanisms, learning mechanical principles. Teenagers design original CAD models, test them through simulation or physical prototypes, identify failure modes, and iterate improvements. Teenage activities should produce portfolio-quality work demonstrable to external evaluators, documented GitHub repositories, technical science fair presentations, CAD portfolios with engineering rationale, competitive robotics experience, because the goal shifts from developing STEM interest to building STEM competency that opens career doors.
Bottom line, teenage STEM activities worth investing in teach industry-standard tools through project-based work that produces documented capability milestones. Whether your teenager is programming microcontrollers in Arduino C++, designing parametric mechanical parts in Fusion 360, training machine learning models in Python, or collecting calibrated environmental data for citizen science, effective activities mirror professional workflows and build transferable skills. Choose platforms with offline capability, open source foundations, and massive expandability. Arduino ecosystems, Raspberry Pi projects, FDM 3D printing, and Python data science all fit this profile. Budget $800 to $1,200 startup across multiple domains, with $50 to $100 monthly for consumables. Prioritize deep mastery over surface-level dabbling, and make documentation and version control non-negotiable practices. The outcome isn't just technical knowledge, it's a portfolio of demonstrated capability that colleges and employers recognize instantly. Teenage STEM work should feel like apprenticeship, not entertainment, because you're building the foundation for climate-forward, technically sophisticated careers that matter urgently.